title of my talk probably represents the fact that I didn't know what I really wanted to talk about when I had to send this title in. Probably almost everything I'm going to tell you we've touched upon to some degree or another already today, so this is almost an immediate retrospective. We'll see how it goes. Hopefully I'll have a couple of new ideas to present as well. I'm starting off with this, one of my favorite diagrams ever published in the literature, and this is by Poirier in 1994 when he did this really excellent review on what the light element in the core might be. And he plotted the number of articles published up to that point as a function of time. And it really is kind of representative of the popularity of those elements in terms of what people were thinking about. So in 1994, sulfur was maybe the number one choice, and then oxygen and silica, and it changes with time. Silica, for example, starts out being the most popular, and this, you might call this the Ringwood effect. He published a paper in 1959, said silica may be in the core for various regions, and boom, it's the most popular all of a sudden. Now, if we go to Web of Science and redo this again, possibly after today, especially what we've heard from Bernard, I reckon silica is going to be at the top of this list. So you can actually do science by just looking at citations and numbers of papers being published. We're going to back up a little bit, take a look at what this core density deficit is all about, and again, we'll come to a couple of ways to maybe how we can constrain it, both from observation and experiment and a little bit of theory. Again, this is density versus pressure. This is just cold compression of iron. This is just showing where this density deficit comes from. And then we compare it with a model for Prem, and we see there's a big difference. Of course, this is at 300 degrees Kelvin. You add some temperature and you expand the iron. It becomes less dense and closer to pure iron, but still it's a long way off. And you end up with something like 10% density deficit in the outer core. And I'm going to concentrate primarily on the outer core. And 2, 3, or 4%, I've heard those numbers bandied about today for the inner core. And maybe I'll just cancel that. If I would have asked people in the audience what the core density deficit was, the outer core density deficit, this is probably the number you'd have given me, 10%. And I think the first thing to do is to take a look at that. Well, actually, the second thing to do after I show you this diagram, which just describes why the outer core is probably less dense than the inner core. It's very explicable in terms of phase relations and partitioning. If you have this is iron carbon at 1 atmosphere, I'm going to tell you carbon's probably not a very likely element in the outer core, but it's a good phase diagram to explain it. You start to crystallize the core and the liquid partitions. The carbon goes into the liquid relative to the solid, and so you end up with an outer core out here and an inner core here. Okay? We'll come back to some phase diagrams later on. But we should look a little bit about this number 10% first, because it's quite important when we start thinking about how much we're going to stuff into the core. If we say 7, 8, 10% silica or oxygen, is the density deficit really as great as we think it is? This is a paper by Anderson and Isaac in 2002. Here again is the 300K isotherm. And they've plotted a number of different temperature contours on here, again compared to Prem. And you'll see that the density deficit is highly sensitive to the temperature. And temperature is something that we don't know very well for the core, and that's because we pin that to the melting point of iron or an iron alloy at the inner core, outer core boundary, and there's large uncertainties on that measurement. And also there's significant uncertainties on the thermoelastic parameters that you put into any equation of state for the liquid to derive the densities in the first place. In this particular paper, they argue that we probably overestimate in general the density deficit, and it's somewhere probably between about 2 and 7%. So I think there's clearly more work to be done here. Clearly, if it's on the order of 2 or 3%, then you can't stick 7% silica in the core. Okay, so it's a very first-order constraint that probably needs more attention. Part of that is because iron melting is still a messy business. Working on it for a long time. I think LaDunca had this diagram up earlier as well. This is pressure, temperature. Here's some initial DAC work with a very high temperature. If you do a sort of a Lindemann law on that, you'll be up here 7,000 degrees Kelvin at the inner core, outer core boundary. This is Reine Bowler's later work, and of course you see that it goes to about 4,000 degrees. So there's 2,000 or 3,000 degrees of uncertainty right there in the temperature at the inner core, outer core boundary. Interestingly, this is the shock data up here. There's 2 sets of first principles calculations. one which matched nicely with the high temperature experiments and one which matches nicely with the low temperature experiments. So that's kind of where we're at. So I think that uncertainty, the first take-home message in a way, is that uncertainty is still so large that placing any tight constraint on the density deficit of the outer core becomes difficult. It's probably somewhere between, say, 3 and 10%. You can then take an estimate of what the temperature is. This just shows an example of how much the light element varies as a function of that temperature estimate. This is the weight percent of the impurity element versus core density. Here are a number of different plausibly reasonable temperatures for the core. Oxygen, sulfur, and silica, if those were the single elements causing the density deficit. And you see, for example, in silica, between those temperatures, it ranges anywhere from 12% down to only a few percent. Okay, so again, it's just sort of illustrates the importance of knowing what that temperature is. We saw this diagram already. I think I'll pass right through that, except for to say that on the basis of these mineral physical arguments, the value which seems to be the chosen value, and I don't think has changed after what I heard today, is around 2% silica in the inner core. And if that's the case, based on partitioning, the outer core has something like 1 to 4%. I don't think we know that partition coefficient that well, but clearly something's not quite jiving together if we need 7% silica in their core. So these things still have to come together and converge. Bernard touched on this, but I think one of the better ways to get to what the light element might be is to start with the geochemical model. This is sort of a cosmochemical model, really, if you will. This just shows the silicate earth. This is an estimate for bulk silicate earth, again, based on measurements from primitive peridotite, relative to a chondritic abundance, CI chondritic abundance, which is taken as the primitive solar nebular composition. This is plotted as a function of condensation temperature. Okay, so the refractory elements are over here. This is the volatility trend for Earth based on lithophile volatile elements, and then there's a whole bunch of things that fall beneath that. Okay, now there's a couple of reasons I wanted to point this or put this diagram up here. One is that if we look at one of the key candidates, sulfur, it's down here relative to that volatility trend. So if this is really plotted in the right place, and there are some uncertainties in terms of when sulfides precipitate or condense out of the nebula, but if this is approximately correct, then we need about a couple of weight percent sulfur to go in the core. Okay? Carbon and hydrogen, which are often touted as the other sort of volatile elements that may be in the core, they're over here somewhere. And so to first order, they're probably not in the core to a large degree, although we can't say that for sure. We really don't know what the impactor materials were. Some of them may have brought in a lot of water, especially late, or carbon, and if you can bury that in a magma ocean and store it in there, and Mark Hirschman has some great new ideas about the ways you might pump carbon into the lower mantle if you have a stable lower mantle phase there. I'm being told to come over here. And then you could possibly end up with more of these volatile elements in the core. But to first degree, we're going to suggest that they're not in the core to any large degree. So sulfur, yes, I think some sulfur has to go in. Now, if you look at silica up here, you'll see that it's just slightly below magnesium, and this is what Bernard was talking about earlier. This is basically the deficit that we observe in the mantle in terms of the silica-magnesium ratio. Okay, the magnesium-silica ratio of the mantle is greater than chondritic, and if you want to make that little change, because there's so much silica in the mantle, 45% by weight in terms of the oxide, then you'd have to stuff something like 6 or 7% of that silica in the core to bring that back up to the value of magnesium. Now, one other argument for that discrepancy there is that silica may be slightly more volatile when it condenses in the nebula, and therefore the Earth just never received a chondritic amount of silica. So if you assume, again, that silica is in the core, and that's what a lot of the models do, then you can say, well, my mass fraction of silica has to be around 7%, and in order to create the rest of the density deficit, assuming a 10% density deficit, then we can say, well, if it's all oxygen, it has to be something like 6% oxygen, if there's a couple of percent sulfur, which is what the cosmochemical models say, that we can just come right up here and we can find that we need about 4.5% oxygen. And that would be our silica oxygen sulfur cocktail, which would make a 10% density deficit. And that's what these kind of models have done. So this is the model from a leg in 1995, and you'll see that this model for the silica content of the core matches very well with Bernard's. Maybe we didn't need to make all those isotopic measurements. We had it all right here. Sulfur, a couple of weight percent. Again, that's based on this volatility difference, and oxygen just makes up the rest of it to get to a 10% density deficit. Again, a number which is relatively uncertain. And here's another recent estimate for the core based on an entirely different bulk Earth model, and that is a model of that the Earth condensed primarily from enstatite chondrites. Okay, and again, you see that there's around 7% silica in the core, so that seems to be a recurring theme. This shows the results of some calculations that were alluded to earlier. This is by Dario Alf. These are a series of publications in the early 2000s. These are ab initio, and what they have sort of settled on is that the solid inner core, so they're really interested more on the density deficit in the inner core, and there's a lot of silica in this particular model, silica and or sulfur, some comps either or both, with very little oxygen in the inner core. And then the outer core liquid that you would calculate to be in equilibrium with that on the basis of partition coefficients, which are not tremendously well known, would be around 10% silica and 8% oxygen. Okay, so that's a lot of silica and a lot of oxygen in this particular model. The point being here, the need for the oxygen is because if your light element is just silica or just sulfur, because they partition about the same between the metal and the liquid, you wouldn't get the big density difference that you see between the inner core and the outer core. So this is sort of the necessity for having oxygen, because it seems to be the one that partitions into the liquid very, very strongly relative to the solid. Okay. So let's look a little bit more at some phase relations. I love this quote from the 1994 paper. The most valuable information on the possible compositions of the outer core comes from phase diagrams of binary, ternary, and quaternary iron light element systems at pressures up to the inner core boundary, which is music to the ears of any experimentalist who likes to make phase diagrams like myself. So we'll just take a very quick look at what we know about these phase diagrams at high pressure, which actually isn't a lot because they're very difficult to make. I'm going to start with carbon, just because it's one that my student worked on for a couple of years, and just based on measuring melting curves of different carbon species, for example, iron carbide, the eutectic between iron carbide and iron 7, 3 carbon, we can then make estimates of what the phase relations in the binary system must be at higher pressures. We also used a radiographic imaging technique to look at what the composition of the eutectic liquids were as a function of pressure, and you see that at low pressures you have a eutectic with around 4% carbon, and that goes to almost nothing, so the eutectic is shifting way over towards iron with pressure. These are a couple of extrapolated diagrams at 50 GPa and 130 GPa, so that's the core mantle boundary. And what I really want to show here is we've got a lot of dotted lines on these diagrams, but is that the core phase, if there was any significant carbon, would not in fact be iron 3 carbon at core conditions, at inner core conditions. It would probably be this iron 7 3 carbon. And if that were the case, the liquid would almost certainly have much less carbon in it. Okay? It does depend on bulk composition. If you had a lot of carbon, you stabilize this phase, then the outer core would have less carbon than the inner core. Some recent first principles calculations on the elastic properties of iron 7,3C suggest that maybe 1 or 2% carbon or that phase could be in the inner core. If we move on to sulfur, we don't know a lot about sulfur at core conditions. This is some work by Fay et al. In 1997. What you see is that the eutectic, although it moves to lower sulfur contents, and we've done some in situ radiographic work, which also again shows that you do move, this eutectic does move and seem to flatten out at around 12 or 15% sulfur. The point here is that, yeah, you can put a lot of sulfur in the core if you have it. The phase relations are certainly there to do that. Silica, this is a very complicated diagram at 1 atmosphere, and we don't know a lot about it at higher pressures yet, but the important thing to look at is this binary loop right here. So once again, you can put a lot of silica into the core, and the partitioning between the liquid and the solid is very close. Okay, so that binary loop is very small, so that whatever amount of silica you think you're putting in the inner core, you haven't got a lot more than that in the outer core, which I think is something of a problem for 7% silica in the outer core, unless we don't know the partition coefficients correctly. This phase diagram may change considerably at 300 megabars. What we have done is to look, and this is some work that Ollie's done, it's in prep, and also some work from Hirose's lab, looking at the eutectic in the iron silica system, and it seems to be going to higher silica contents rather than lower silica contents. So I think there's no problem in getting silica into the core. Oxygen is an interesting one. It's one that's fascinated me for a long time, and I still don't quite understand it. At 1 atmosphere, the eutectic is way, way over here. You just cannot get very much oxygen into a 1 atmosphere iron liquid unless you go to very high temperatures, so you'd crawl up this liquidus right here. Even so, you can look at the fractions here, and they're relatively small. In a really nice in situ study, it seems that this phase diagram changes a lot as a function of pressure. So here is the phase diagram now at about 55 GPa, and over here we see the tracing of the FeO eutectic liquid as a function of pressure. So at low pressures, 1 atmosphere, very little oxygen goes in, and the eutectic shifts to much, much, much more. So here's an example, a great example of where the phase relations at high pressures are significantly different than they are at low pressures. And in fact, initially, 50 years ago, when they started thinking about oxygen as a possible element in the core, and the ideas then were that the Earth was accreting through sort of a gentle addition of material, and so there's a lot of low pressure equilibration, then oxygen was not a very viable candidate. Of course, at higher pressures and temperatures, it becomes a much more viable candidate for a light element, and we'll look at that more soon. Okay, so that's sort of a run through what we know about the major candidates. I've probably missed a few things, but that's the general picture. What I want to do now is I want to kind of take a look at what can we do in terms of observations, and we've heard, of course, some of this already, to place real constraints on what's in there. And I think I've avoided the isotopes simply because I knew that Bernard was going to be talking about that, and I think the isotopes are an absolutely fantastic constraint on whether there's silica in the core, for example. There's a couple of other things that we can use. One of them is siderophile element partitioning, and I'll go into that, and Bernard's touched on that as well. Another one is seismological observations. I'm not an expert at this, but my colleague in Bristol, George Helfrich, has been doing this, and so I thought I would talk about this a little bit. And that's because as we crystallize the inner core and we release the light element into the outer core, it's possible that you might have phase segregation of that light element in the outer core if, 1, there's saturation of that phase, and if, 2, there is immiscibility. And immiscibility is something which is very common in iron light element systems. So we'll take a little bit closer look at that. The idea is this: you crystallize the inner core and you increase the light element in the outer core until you hit a 2-liquid field. And if you hit that 2-liquid field, then you'll have one liquid which is very enriched in the light element, one which is less enriched, and that particular liquid might be less dense and would move, and you might be able to image that seismically. Okay? Move and potentially pond, for example, at the core mantle boundary. So this diagram shows percent difference from Prem, okay, and height above the core mantle boundary. So this is going into the core, and that's in the mantle. There's Prem, and here are a number of other one-dimensional seismic models, and we see that there seems to be this velocity change and this velocity gradient, which is the big thing, as you go in the first couple of 100 kilometers beneath the core mantle boundary. All right, and these are imaged, I understand, from these sort of underside converted phases, these converted shear wave phases that bounce along the underside of the core. And seismologists here can tell me whether these are reasonable or not. So what George has done, George Helfrich and his colleague Kaneshima in Japan, is to try to model what would do that. Okay, so that's an observation now that you can link to composition. Now, of course, what we really need at core conditions are complex quaternary phase relations for iron, silica, oxygen, sulfur, and maybe add in some carbon and hydrogen. We don't have those, and we're quite a ways from having those. So what George has been doing is trying to calculate those from a thermodynamic model. And this is models which take into account a lot of one-atmosphere data, extrapolations to higher pressures and temperatures, and the building up of ternary phase relations in this way. They've concentrated so far on iron, oxygen, and sulfur because from the metallurgical data, that's where you have the best thermodynamic data. They're moving into systems involving silica now, and we're trying to provide high temperature and pressure data for them as well. The bottom line is that in order to match that velocity gradient relative to Prem that they observe from seismology, there are only a certain number of compositions that can do that in terms of the velocities, because they also calculate the P-wave velocities that you get from that. And so this is the liquids that they calculate. So you see that they have something like 3 to 5% oxygen, and they're relatively sulfur-rich. Okay, whether or not that matches with a cosmochemical model is a different question, but I think what I really wanted to point out here is this is the kind of way forward. If we want to really constrain what the light element is, then we have to have an observation to match, and a seismic observation together with phase diagrams is one way to approach that. Okay, so I'm going to finish with another way to approach that, and that's with siderophile elements. We've heard something about that already. Again, another very prescient statement from the Poirier paper. The nature of the light element is tightly linked to the mode of formation of the core. Okay, and that's because the light elements that went into the core clearly would have done so on the basis of their solubilities at the pressures and temperatures at which the core-forming liquids equilibrated with the mantle. Okay, not at the core conditions now. So what we can do, if we know the way the core formed, and we can constrain the pressure, temperature, oxygen fugacity path of that core formation, and then we can tie in a model that involves oxygen, silica, carbon, whatever solubility, then we can make an estimate of what the core liquids would have been that we're segregating. Okay, and we do this through this group of siderophile elements. So basically everything that you see beneath this line probably is beneath that line because it went into the core. Okay? These are the ones that we normally work with in terms of siderophile element models because they're refractory and we don't have to worry about this business of what the volatility curve really is and what that difference really is. And we typically look at nickel, cobalt, tungsten, molybdenum, this whole suite, and recently elements like vanadium and chromium, these so-called slightly siderophile elements, have been producing some of the tightest constraints on what core formation scenarios were. So we're going to take a look at some models to produce these and then see what the oxygen and the silica do in those models. So the idea here is, I didn't realize I had this fancy stuff, is that you make an experiment, you have a silicate liquid, you have an iron metal blob, you have a suite of elements, or one element, depending on how you do it, doped in this experiment, and you go in with a microprobe or a laser ablation ICP-MS, and you analyze the abundance in there, and you analyze it in there, and you get a partition coefficient. And that tells you, as a function of a whole bunch of variables like pressure and temperature and oxygen fugacity and the composition of the liquids, that tells you how those elements partition. So you have this D value, and then you have a model value for the Earth's core and the Earth's mantle. So you might call that an Earth D, okay? And that's based, again, on that. So the Earth D is simply based on the difference between where we think it should be in terms of a chondritic bulk Earth and where it is in the silicate mantle, all right? So then it's simply a matching game. Okay, we've been playing these matching games for a couple of decades now, and the matching games get considerably more sophisticated, as you saw earlier with Bernard's talk, as time goes on. 15 years ago or so, when people first started looking at the effect of pressure and temperature on elements, it became apparent from nickel and cobalt that these elements did not match well for a low-pressure core segregation model, but if you include the effects of pressure and temperature, they conspired in such a way that they crossed at a value which would match the core mantle equilibrium value, the Earth D, if you will, at some high pressure and some high temperature. Okay, so this was the first evidence, really, that core segregation has this high PT component to it. Since then, and this is a very voluminous and growing literature, there have been lots of estimates of what the conditions of core formation are, and this is a temperature-pressure diagram which sort of summarizes on the basis of lots of different studies, and each one of these studies has sort of a different suite of elements that they're looking at, but you get the idea that somewhere between, say, 20 and 60 GPa and 2,000 and 4,000 degrees Kelvin is where the core forms. So it is high pressure, it's high temperature. There's lots of uncertainty in these models, which I won't go into. But this ends up in sort of what became the standard model of core formation. Bernard also sort of talked about this, where we have raining out of metal, materials coming in, splashes down, metal emulsifies in the magma ocean, re-equilibrates quickly as the drops sprinkle out to the bottom of the mantle. There's a magma ocean floor, a solid silicate magma ocean floor. You end up with a pond of material, and that sort of gives you the final equilibration depth because these things are re-equilibrating as they fall through the mantle. And that's kind of the single-stage core formation model. And when you do that, again, you end up with something roughly around 40 GPa and say 3,000 or 3,500 degrees Kelvin, plus or minus 10 GPa. Now the question is, if that's our conditions of core formation, what would be the silica and the oxygen content of those segregating liquids? Okay, so here's some experiments which were done by the group at Sendai. This is silica in liquid iron, and this is as a function of this parameter FO2. The Earth, if we take our bulk Earth model and we say the mantle has 8% FeO and the core has 85% iron, and it's an ideal FO2 for the bulk Earth, that gives you about iron woostite minus 2.4. Okay? So if we had a one-off model, you have to end up with iron woostite minus 2.4 for our bulk Earth. Then this tells you that at high temperatures, this is not quite 40 GPa, but it's close enough. Some of the models even suggest core segregation around these kinds of pressures, that at high temperatures that you would end up with about 3% silica in that particular metal. And if you do the same thing for oxygen, which is shown over here, so here's again iron woostite minus 2.4, that you have, say, something like around 1% less oxygen in that metal. So this is obviously quite dependent on FO2. If you go to much higher FO2s, cores which are segregating at high FO2s, maybe late addition core material, for example, then they can have a lot more oxygen in those metals. If you're at much more reducing conditions, like Bernard talked about for the early part of accretion, then you can put a lot more silica in, say 8, 10 weight percent. So when you do that, and this is actually from theory, but I think it actually matches very closely with what we expect from experiments like this. If you have this one-off model, say a temperature of 3,000 degrees, a pressure of 37 GPa, then you end up with something like 5% silica in the core. That's probably a bit much for iron woostite, minus 2.4, but you don't have a lot of oxygen, okay? I just wanted to point out, if that is the case, all right, this is just a slight bit of an aside, if core formation occurs down here at around 40 GPa, and if we're putting, say, a couple of weight percent of oxygen, these are DAC experiments, quite uncontrolled in terms of what the actual FO2 is in these experiments, but this shows a pressure effect on the solubility of both oxygen and silica in core liquids equilibrated with silicates. And it seems to go to much higher solubilities at high pressures. And if you extrapolate that to core, then you can stuff a lot of these things in at very high pressures. The point of this is that the outer core is likely to be very undersaturated with respect to these elements, and especially undersaturated with respect to oxygen, so that the core should be actually dissolving the mantle rather than vice versa. Okay. Single-stage core formation, probably not the most realistic scenario in terms of how we understand how planetary accretion works through the accumulation of, first of all, lots of small planetesimals impacting upon each other, and then at the end of accretion, perhaps giant impacts and punctuated growth history, perhaps at the end, especially with a very large moon-forming impact. So we're going to look now very quickly at this more complex accretion scenario, and also what Bernard's also alluded to, this business of a changing FO2 as a function of the accretion history. And this first came about with some observations from Wade and Wood, where they noticed that, yeah, if we can do these single-stage models and we can match, say, 6 or 8 elements, but when you do that, for example, you might get a pressure of around 35 GPa, but a temperature that doesn't make sense in terms of what the temperature should be at the base of a magma ocean. Because if you've got a magma ocean, a liquid, and then it's got a silicate interface, that defines the liquidus of the material, doesn't it? Okay, and so they said it really should be down here on the peridotite liquidus, and we're several thousand degrees above that. If we want to have it, if we want to bring the equilibration down to the liquidus, then it doesn't work. And especially doesn't work for an element which is vanadium. And that's because vanadium shows virtually no pressure dependence, a relatively mild FO2 dependence, but it's quite temperature sensitive, at least in these particular models. Here's a more recent rendition of this in kind of the same way from Julian Siebert's work. Pressure, temperature. What you're looking at here is the range of solutions for a whole suite of siderophile elements that fall within about 40 GPa and 3000 Kelvin, and then all these other bands that miss it are the misfit elements. Okay, none of those work. And you see vanadium is way over here. And these big bands are because there's quite a bit of error on these partitioning data. Okay, and if you do sort of a Monte Carlo simulation and really show what the error windows are, you find that, well, you can almost do it, but not quite. So you miss for a bunch of elements. So the way forward then is to see if you can produce these elements with more complicated models. And so the models that people have developed are for as the Earth grows, the average depth to the base of the magma ocean increases, and so the pressure and temperature follows a liquidus path as a function of the size of the growing planet. So the pressure is given by the base of the magma ocean, and you know where the liquidus temperature is then, so you can just use that path and look at your partitioning as a function of those variables. Now, if you do that at a fixed FO2, which gives you 8 weight% FeO in the mantle, what you find is that, yeah, it works for a number of elements, but it doesn't work for vanadium. You're something like an order of magnitude off for vanadium. Now, there's actual uncertainty here, quite a bit of it, and I've done this model for vanadium and put in all the uncertainties, and it turns out you can make a match sort of at the tail of a Gaussian distribution. It just depends on how comfortable you feel with that, I guess. So what Wood et al. Did is said, well, okay, if we want to put vanadium into the core, the problem with it is it's too lithophile in our models. We need to make it more siderophile. And a good way to make things more siderophile is to make things more reducing. Okay? And at the same time, this particular model produces almost no silica in the core. So if we believe the earlier cosmochemical constraints that you need something like 6 or 7% silica in the core, a great way to stuff silica in the core is to make things more reducing. So this is quite an appealing thing to do, and what they've done is a progressive progressively more oxidizing. You start out with the very reducing, something like iron woostite -4, and you end up with the current FeO content at the end of the model. And what they showed was for a whole range of these elements that you can, in these kinds of models, that you can then reproduce the whole suite, and you can get vanadium just right and tungsten just right, and all these things come out in the wash. So what does that mean? And here just shows an example from Julian's work. For vanadium, again, fraction accreted, and the point is that as you're moving from here to here, you're getting progressively more oxidizing. I think this may have been a step model. It looks like there was a step around 25%. And at the end of this is what happens if this is where you need to be for vanadium. This is if you have a constant FO2, which is iron woostite -2.4, and this is the progressive accretion model. And you see you start out with actually too much vanadium in the core, and later on you bring it down to the value that you need. So how does this play out then for our light elements? And this is some recent work by Ricolo et al., where on the basis of experiments, both in multi-ample and diamond-ample cell, and parameterizations of the amount of oxygen and silica that go into the liquids as a function of PET and FO2. And if you trace some of the models that other people have done then and use those same types of parameters in terms of the way FO2 changes with degree of accretion, and I think this particular panel goes along with C. So fraction accreted, and this is log FO2 relative to iron woostite. So starting out very reducing and then moving up progressively to the modern Earth value. This is what happens for silica, and you end up with about 5% silica in this model, and this is the error envelope based on the parameterization, and then you end up with oxygen at around 1%. Okay, so that's kind of where I think we are. Obviously, the isotopes play into this very neatly, and the isotopic composition, the silicon isotopic composition, really does seem to require silica in the core. But I would reiterate that we really don't know that value as well as we would like, and I think it's a big issue of uncertainty still. But at the end of the day, and the take-home message is that silica seems to be leading the pack now. Probably around 3 to 7% silica would be a guess in the outer core, maybe 1 to 4% oxygen, and I would maybe take that down a little bit, a couple percent sulfur on the basis of the cosmochemical arguments, and these guys are less likely. And I'll stop right there. Thanks.